So, hello guys, and welcome to this video about race conditions. We're going to talk about race conditions and how dangerous they are in your program or software. So let's start with the first case. I'm going to bring my outline here so I don't get distracted. The first race condition I've ever learned about, it was when you have a distributed system or a serverless architecture, and you have two running instances or two different programs trying to modify the same exact resource. For example, I can't think of a good example here, but I know this one is bad, but yeah. You want to increase the number of fetches or accesses to a file. Let's say, for example, you have a file stored in S3. For example, a user image or a user birth document or whatever. And whenever one of those server tries to access that file, you need to increment the counts. So you need to read it. Let's say you're not using a counts that's managed by Redis like you do. Count, I guess it handles this thing automatically. Let's say you're doing a read, you need that read for something. Let's say you update the file with its visit count or fetch count. You're gonna read the file so you can increment it and add that number as a suffix to the file and then re-upload it again. That's a bad thing. Never do this, but just for the sake of the example, like I've seen some systems which do this. Maybe there is no other way around it in some cases. Anyway, to manage this, you basically use locks, and just locks are what they are, You use, for example, Redis or Memcached to create a value, for example, the file ID or whatever. If you have a user ID and dash the count, you do the user ID and you put whatever you want in the key value in Redis, like user ID 1 or true or whatever you want. It's just there, and of course you add a TTL to the cache so it expires in case the system fails to remove that lock or release that lock after it finishes. Sometimes it can happen, and you'll stay with a lock, and your other backends will never access that file because they see it as locked unless you see your logs and or a bug report, and that's very nasty. You never want to fall into that problem. So the second one I noted here is I try to collect cases here and there which are race conditions in databases. I've done this multiple times, like in the past, many years ago. I've done this when you have a user credits or balance or whatever. You read the value and you need to read it and do an operation to decrement that. And if you have two parallel executions that are accessing the same row at the same time, that's a very bad problem. You never want to fall into that because they will update the same thing at the same time. If you have value 1000 and you need to increment it by 1 and decrement it by 1, you're basically gonna be left with 1001 or 999 instead of 1000, which should be the real value in there. And this is in Postgres. It's called row level locking. I don't really remember the details of it. I just try to note the cases here so I can go scan through them very fast. So basically in Postgres we do a select for updates. So and there is a difference between select for updates and select for share, because when you do select for updates, for example inside a transaction, nobody can access that row. No other connection can access that row unless the transaction commits or fails, which is rollback. But select for share is very useful. For example, when you want it, select for share forbids writes, but it allows reads. If you have an account balance on your bank account, for example, you need to be able to read the balance to display to the user while it's being written to, it's being updated. That's very important. If you do a select for update, I guess it doesn't allow reads. I don't know. I think it does not allow reads. I never really did this to begin with, to experiment, but I will experiment after this video for sure. Yeah. And you do row level locking transactions. I'm just trying to scan over all the use cases that I have in my mind, so we don't make a really long video here. I hope the voice is clear. I didn't really test. Yeah, and we can have deadlocks in this. For example, when you have just like OS trading, or just like Redis, it's basically the same thing. It's universal. When you do, in the first example we talked about, when you do a lock and your backend 1 is modifying the value, the backend 2 just waits for it to release that lock. It just keeps polling. Are you finished? Are you finished? Are you finished? You define an interval depending on your transaction, of course. If it takes 6 seconds or 300 milliseconds, who knows. And it's the same thing for Postgres. Like when you do updates where ID equal 1 or equal 2, and another transaction is trying to do the same thing. They started at the same time, but one will fail. It will throw an error. Okay? Because it basically cannot do that. Another transaction is handling that updates, or doing that updates. Your other transaction cannot. So that's why you should have retry mechanisms and so on, or just at least show the user feedback that, oops, please try again. It's our problem, not yours. If you don't want to retries, because retries are nasty too. They can result in different problems. They should be carefully implemented. Our third example, which I recently learned about, it's not something I fell into. Like, I don't code on the OS level. I hope I can do that someday, but not yet. Which is multi-threading. When you have a multi-threaded program, we know that threads share memory. Okay? When you do a context switch on a thread, you're not flushing all the CPU registers. You're just flushing the program counter and you're giving it a new place in the stack, I guess. That's it. I didn't really just, if I have a good memory, I guess that's it. You keep all the other registers But the most important is the TLB, which holds the cache for mapping between virtual memory and physical memory. And that's another topic when you can do a video about it in the future. So when you have two threads sharing the same memory, and guys who did multi-threaded programming can talk to us in the comments and explain this in detail, or just give an example or share with us their experience, of course. And as I said, when you have two threads that are trying to access the same variable or modify the same variable, that's problematic, because the old one still holds the old value, and you're gonna fall into the same problem. So in the OS level, there is something, or there are two things. Let's talk first about mutexes, which are just integers, just like the case in Redis. We just do an integer in memory 0, 1, but it has the thread that holds the mutex, it holds the ownership of that variable. Like, I have the ownership of that variable. No other thread can access this one. You wait until I finish, and when I finish, of course, I'm gonna release the lock. But there is another concept, which is semaphores. To give a concrete example, this one is very common. Like in the book I read about this, they gave this example of Postgres. For database connections. If you have a maximum of 6 or 7 database connections, you will have the semaphore initially as a variable incremented to 6, and whenever your server accepts connections, a new connection, it decrements the semaphore. So it's now 5 until it gets to 0. So there is no ownership here. When I finish, I just boom, decrement. I don't hold that exact value. I just increment or decrement. When I finish my connection, I say, hey, decrement this one. So the other ones that are waiting can access this, can accept connections, or my server can accept more connections. And that's very useful. Everything in software is a trade-off, of course. Let me see if I forgot anything. Semaphores. Yeah, of course, in the next videos, it just came up to mind. We can give more examples, because race conditions are everywhere, and you might have implemented them in the past. Just go scan through your old code. You'll definitely find yourself doing race conditions, especially if you're dealing with databases or I/O stuff. Everything that has I/O will definitely result in race conditions. Yeah, we can do race conditions in, I don't think we can name this a race condition, but yeah, it causes a big problem, which is in the CPU. You have the CPU cache, the L1, the L2, the L3. Apple Silicon actually doesn't have an L3 cache. It just have a large L2, I guess. Yeah. So when you have a cached value and you modify it in your code, and it's there in the CPU cache, and you have 3 layers, each one is separate. How do you manage this inconsistency? If you have it in the L1 and the L2 and you modify it, that's very bad. That's very, very bad. So how do we deal with this? We can keep it for another video, because it's a little bit complicated. And yeah, a bonus section is, I don't think this is also a race condition, but I'm gonna say it anyway. In Redis, you have you're writing to disk asynchronously. Redis is in memory database. So if your server shuts down, it's gone. All your data is gone. So you need to flush everything from time to time asynchronously to not block your program to disk, to write it to disk. So in case your server shuts down, you can at least load whatever data was written into disk on that moment. That's why also your cache keys should have a TTL. Okay, please, it's very important, because it can expire even if your server is gone or whatever. You're not depending on the cache 100%. You go and if you get a cache miss and you do a cache hit, you fetch the data and you load it into the cache. So what Redis did is to write to disk asynchronously is to fork a process. And when you fork the process, the child and the parents share memory. Here is the catch. If anyone tries to modify the memory variable, let's say variable, which does exist in the memory, your first process, your parent process, or let's say the child in this case, because in Redis you're forking just to flush to disk, but the parent might be updating in the background, might be updating those variables, and our processes share memory. So in this case we do a copy on writes, where the kernel says, okay, parents, you want to modify this thing here in the memory? I don't care. I just grab it. It's called copy on writes. Copy on writes. I don't copy until I try to write. I hold this value. I move the original value somewhere else to memory, and I just update the pointer here, point to this address. That's it, I guess. Maybe I'm wrong here. For people who are deeper in the low-level stuff can correct me, of course. And that's a copy on writes. And that's very efficient, because you're not duplicating memory unless you need to. So I don't think if we can call this a race condition or not. It's just an inconsistency. And it exists also in Postgres when you're updating something in a transaction. And in the transaction, let's say you're reading it, you're doing an operation, and then you're committing. If another value tries to modify something or access, let's say access something, it will get the old one if you did not commit yet. Because what Postgres does is a snapshot. But I don't really know how they manage the writing case, because if you just read, it's fine. But if you want to write something, we need the old value, because we don't know what your transaction is going to access. It can access or depend on another column right there. We don't know. Accounts or transactions or whatever. And it should have the exact value the moment of the transaction. The transaction will start at the begin. I don't know how they do that snapshot, because they can't duplicate the entire database. That's stupid if you do it. You have hundreds of transactions, and that's not even doable in the first place. I guess they do something like the copy on writes, where they don't modify the values in memory and on disk. They modify them in memory and they point the new ones. Maybe, I don't know. I'm just guessing here. I will definitely try to research this topic after this video. It's interesting. So yeah, that was it for today's video, and I hope you enjoyed. See you in another one.